Hello, everybody. Hopefully, you can start to hear me. Again, it's always interesting when I have to keep an eye on the earphone about 20 seconds ahead of you. So it's just one of those things I'll have to deal with. have a look in the chat, and I did test this just a moment ago, that you should be able to click on the link for the coding website that we'll just have a look at in a moment. Feel free to do the quiz as we go and then do it again to test yourself. And we're going to have a look at a few different ideas today on the chat, a little bit of history and a little bit of future as well to go with it, and understanding why how computers work and how we program them and how it's changed over the years. So to have a look at that, I'm going to have a look at this little presentation, a brief history of, sounds really dull, but it's actually, I think, quite interesting. But we have to know the terms, compilers, assemblers, interpreters. Before we kind of get to that, I suppose, just a little reminder, I suppose I will do that. Just a little reminder that you've got this website here. Like I said, have a go as you go through it. You can get to it directly doing digital.edu.je or click the link in the chat that we have there. And the quiz will be found on the quiz page for software development. So feel free to open that up and have a go maybe as we go, as you see the answers as I talk about them as we go through. So I'm not going to waste any time. I'm pretty much going to talk to you about the fact that if you like playing games, you need to know a little bit of history about how you're able to do so cheaply. So what we're going to have a look at here, like I said, is this talk about compilers, assemblers, interpreters. But we kind of, before we get there, we're going to have a talk about machine code. So machine code is a term you may have heard before. It's really, really difficult. Right, so it's a highly difficult skill, and it's basically talking to computers in ones and zeros, the things that they understand. So what we're kind of saying is, back in the day, computer programming was highly specialist. It was really complicated, very, very tedious. You had to type everything and on, off, like a kind of Morse code. And if you wanted to use a different machine, you had to learn a new set of rules and a new set of codes. So it was incredibly difficult to code back in the day. Then something came along that was a little bit easier, but not that much easier. We'll have a look at what easy looks like with assembly language. And so we talk about the 1940s, and things like add and sub for add and subtract came about. And you might think, wow, okay, add and subtract, we're not really talking about anything adventurous here. And we really weren't. The whole kind of concept was that it was incredibly difficult to do that, but these assemblers made it easier to write code in a language that was kind of semi-okay to understand rather than just ones and zeros. We're going to have a little demonstration of that in a moment. So one of the very famous characters in this story is Grace Hopper, who became Admiral Grace Hopper. And she's really there, she was really raised the importance of software engineering, a great figurehead for that. And she's also famous not just for being an absolute pioneer in developing COBOL programming language, something even easier than the thing I'm going to show you, which is quite difficult, and also being a great proponent of software engineering. If you ever hear bug in the code, she's also responsible for that, because when she was working on one of these massive computers, not like the ones we have, where they have rows and columns of transistors and technology, effectively she was going down fixing, there was an issue, and a moth had flown into the system, and she just said there's a bug in the system. So that actually is where it comes from, an actual moth flying in to where we are. So like I said, we're going to talk about what this is. Just make sure the comments there are in tone, not giving anything away. So here we got the interpreters. So once we found this assembly language, as we talked about there, we then talk about interpreters, which allow us to use higher level code, running each line independently, telling us if there's errors, and compilers are the kind of the opposite, and they run everything at the same time. There's times where you would use one or the other, but effectively what we're saying is you need to know the difference between assembly language, just for a tick box question in an exam, that will basically say that was kind of one up from machine code, still not easy, but better than machine code. But compilers and interpreters are what we use now to do our coding and to do everything that you see. So when we use Trinket and stuff like that, it just depends on whether you're doing something line by line, which means it's an interpreter, or you're doing the whole thing at the time where it's a compiler. So in the modern language, we use these things called high-level tools or high-level programming tools, and that has made it even easier. So you might not think Python and JavaScript and HTML might be easy, but they're a lot easier than some of the stuff and the demos that I'm going to show you today. So, like I said, compilers, assemblers, interpreters. Assembler, one up from machine code. Compiler, interpreter is what we use today. One does it line by line, interpreter. One compiles everything in one go. So that brings us to the history of this piece of technology, not the exact one in the picture, but the 6502 microchip. Now, again, this was a groundbreaking microchip that allowed us to afford computing. It was £300 to buy a microchip back in the day. This came in at about £20. And back in the day, that was way more expensive. To put it in context for you, it's like finding out next month that you can buy a top-of-the-range iPhone for £99. That's as big as of a change as it was. Not paying the $1,500, depending on how big you go. This was such a monumental change that it allowed us to, or allowed people to afford the home computer. Before then, people really didn't think that the home computer was going to take off. And so it's a really important piece of history and one that has defined a generation of computing, where it went in the NES, the Super Nintendo, hence giving us Super Mario, or the Commodore 64, which I know. So there's a lot of thing that we give credit for that for. And its influence went beyond personal computers. It went into calculators, anything with a piece of technology in it. But it's most known for going into things like Atari, Nintendo Entertainment System, and other computers. And these kind of things are my youth. I grew up with this microchip. So very, very important piece of technology. But like we said, it's also very important that we remember it didn't just do that. Printers, early technology, and calculators needed this too. And it really had a huge impact on bringing the personal computer into the house, made it easier to learn coding, which was very specialist back in the day. And it's not that easy, as I'm going to show you in a second, but it was a hugely impactful piece of technology and long lasting. There's still people to this day that try and make things for it. It holds a bit of a nuance going forward for everybody. So we'll talk about the fact that it's made up using transistors. All computers use transistors. And it's really, and this is kind of, while I've skipped by a lot of stuff, it's worth taking a moment on this and understanding that back in the day, transistors used to be these big valve type things. And it just used to mean a computer would know what on and off is. And that was how big they were. They were huge things. You saw the picture when we were looking at Grace Hopper in the background, huge computers. And they're the building blocks of ones and zeros, binary. It's either on or it's off. Nowadays, computers have billions of transistors in them, not just hundreds as there used to be. And they use things called logic gates that we will get to with and or not, to do these kind of calculations. And there are people that go into Minecraft and try and make computers in Minecraft using redstone, just using on-off switches. And it has been done. Find a video of it, have a look at it. It's quite impressive to see someone build a computer within a computer. A little bit eerie. And it has tiny parts of memory, momentary parts of memory, not proper memory, which we'll talk about, which is RAM that we use to this day. So huge impact on what goes forward, transistors. And we're going to have a little look at how many are on there. But a very important idea is Moore's law. Moore's law is a person, Gordon Moore, who said that about every 18 to 24 months, computers or the amount of transistors that you could have would double every 18 to 24 months. We call that exponential growth. And it's shown how fast and how good computers have got. And roughly speaking, it's a little bit challenging now due to how tiny and microscopic things have become, that this law has stood the test of time. A huge prediction that stays true largely to this day. It means that in real terms, every time that you buy an iPhone, each maybe 2 years, it's twice as good as the one before it. Now, you might not think that's impressive, but if I put it into context and say, if I had a piece of paper or, I've got kind of cloth here and I fold it in half and I've got two pieces of cloth now, and I fold it in half again, I've got 4, and then I have 8, then I have 16, and then I have 32, and I keep doubling that number. How many times would I fold a piece of paper until that thickness, ignoring the fact you have to stop about 7 or 8 times. I think the world record's about 11, actually. Maybe someone Google it and find out what the new world record is for that in the comments. But how many times, if you could imaginary fold a piece of paper up infinitely, how many times would you fold a piece of paper before it was the thickness from here to the moon? About 350-ish thousand kilometers away. And most people start saying thousands, tens of thousands. It's actually 43 times. Okay, and I kid you not on that. People can start to argue. I've done the maths. It's there. You can Google it. Depends on the thickness of the piece of paper, whether it's 43 or 44, but it's always at that number. And that's because you think about the last fold, it was halfway before that. It was half the distance. The last fold was halfway, then a quarter. And what thank you, 12 times is the record. There we go. But only another few times, we're saying it would go another 31 times and you would get to the moon. And that is a true fact. Like I said, you can Google it. And the reason why I'm talking about pieces of paper and the moon is that I came up with the kind of Nintendo era of computing that was rubbish, barely 8 colors on a screen. And now you look at full VR and you look at all the stuff that's going on in computer gaming now. Every 2 years, that's going to double. So you're going to live through a time of much greater growth with technology because of this law, Moore's law, which still proves kind of true to this day. So we've seen huge, rapid adoption of computing and the microchip. And while it was rubbish to begin with, it is excellent now. So I'm going to do a demo rather than just kind of bore us. We're going to talk about software development in a second. So I'm going to come down and then talk about compilers and stuff like that, just to get us the knowledge as we go through. So I'm going to show the cam and the screen now. I use different compilers. I'll zoom in when necessary. Visual Studio Code, interpreters and compilers. We can use the one we use quite a lot, which is Trinket, to do all of those things. But I'm going to show you an old school bit of code now. So this is the chip that we're talking about. It's a zoomed in version. If somebody's got the Apple Vision Pro in the comments, I'd be very jealous. So well done if you have. But if I zoom in on this screen, as I'm going to just do in a moment, let's do Command Plus. There we go. We can zoom in and see that each part of the computer is absolutely tiny. It's like almost an X-ray version of this. If I was to press play on this, we will start to see all the electrical impulses moving around those transistors. This is how a computer effectively works, sending impulses, doing calculations, and moving that very, 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 very fast. Now, what it can do, and I'll stop this because the computer will struggle to do this over and over again. So I'm just going to stop that as we go. There we go. So how was a computer programmed back in the day? You don't have to do this, but you have to at least have seen it and understand the difference and show how difficult it was to write in machine code. And that machine code is kind of what we were seeing in hexadecimal here at the side, which can be converted into binary, and I'll have a look at all of that. Again, you don't have to do it. You just have to have been shown the history of everything. So here is an example of some code that you might write. Now, what you have to realize is back in the day when things were rubbish, we had 3 of these registered, these things that can remember stuff. And using these things that could remember stuff, we could write calculations. And you would write different calculations called LDA, and you might put the number 1, just moved it out there using my other key to get the hash key. So we have LDA number 1. We're defining these number A, X, and Y. Again, just showing you demonstrations of how bad it was. So we're not having to understand this. And then we would have number 2, defining that we've got 2 registers. And then at the end, we would do LDY, representing this one. And we would say that we had 3 registers. That is it. That is all we are saying. And right now, if we were to say assemble, it would assemble the code because it's an assembler, and we could look at the hex dump of the code that was. That is the code that we've just written. And if I was to zoom in on that, which will probably be quite difficult, but I will try my best to zoom in on that. There we go. If we zoom in on that, that just says that LDA, those words there are, let me move that to the side so I can see it at the same time. There we go. Move it off there, move it off here. So LDA represents this A9. The number 1 represents the number 1. LDX represents A2. Number 2 represents number 2. And LDY is A0, and that represents the number 3. Absolutely makes no sense whatsoever, but a machine coder would know all of this. Try imagining before an assembling code, which still looks absolutely terrible, trying to write something in this kind of hexadecimal binary code. It would be a nightmare. Now, what we're going to do here is just show you that very, very quickly, that if I was to actually store some values, they're known as mnemonics, and we would store them, store A, 5112, store X, store Y, and then if I did assemble this and run it, all that's done is 3 tiny little blocks. That's all it represents. 3 tiny colors that represent it, and that would be the code. If I just refreshed it, actually, sorry. I grab that out again, we might have new code for our hex dump. So all those extra bits represent these. So again, I'm going to wrap this up quickly because you don't need to know it. You just need to see that machine code is a terrible, terrible thing. And if I was to write a large piece of code here to do some random numbers, in fact, I'll show you how it would build up. If I just do copy here, I've got something off screen rather than bore you with all this. And if I was to refresh the screen, just so I can assemble it, there we go. I press run, we have this random dot flashing. If I want to make it look a little bit better, I can make the whole thing do some random pixels. Again, I'll end this bit very, very quickly, just showing you that to write this random bit of code where everything's moving, you can see all these things moving and all the binary numbers changing. And if I stop and do the hex dump of that, we've got the code that references that. But you wouldn't stand a chance doing that. So even this assembler was fairly punchy, and I've done a new version of that microchip just to zoom in, and I put exactly the same hexadecimal code that was in here, and then I can run this, and that was the computer. As I press the plus and I zoom in, this is exactly what this processor would be doing, sending impulses all the way around to make that random color code on a computer. So that's the kind of boring part, but it's a history lesson you need to have seen to understand that machine code, very, very difficult. An assembler adds a little bit of like easier way to write stuff, but is still quite a difficult thing to do. So sometimes you can appreciate that when those games that you see in the form of Mario were written, they were written in assembler language, and each part of those pixels were written in some sort of crazy code to do with what we have just seen. So we should really thank everybody for coming up with things like Trinket, like Visual Studio Code, like all the stuff that we end up using now, the compilers and interpreters that we use. And if I was to write something wrong in this Trinket value here, and just do print with 2 T's, and then see that I've got some errors in there because the computer will write this line and this line, but not this line. I'm going to pause because I'm going to have to fake 20 seconds worth of stuff. If this thing that I'm looking at now will do it line by line by line, is it a compiler or an interpreter? This is the only really big thing. I've talked for a good few minutes now, but the real punchy part that will be asked in an online exam is, what's the difference between a compiler and an interpreter? One does it line by line. One does the whole lot in a piece, and this one has written some stuff but then stopped at this line. So what does that make this? It will be a question in the quiz that's there, but if you want to try and write an answer in the comments, I've kind of tried to fill some time there to try and get people the opportunity to do that 20 seconds behind as I'm listening it now. So nothing yet. Maybe people are a little bit confused. One's line by line. 50-50 chance, isn't it? Compiler or interpreter. One does it line by line. Okay. Now, if you think about the words, I think that you've got an idea. If you think about the English, and this is good with computing, if you needed to guess in the online exam, I think actually you could just think about the words to compile something or to interpret something. If you think about when you're listening to a language or you're doing your French or you're doing some sort of subject, when you're interpreting, are you doing it all together or are you struggling to keep up line by line? There's the clue for you. Something that does it line by line is the interpreter. The compiler does it all together. So I've labored that point a little bit, and I know that bit's a little bit dull, but there are dull parts of the exam that we just have to learn the answer to. Compiler, interpreter, those are the things that we definitely just have to know, and hopefully you do. So that's the kind of like hardest part of doing that. And as you go through the kind of quiz, when we look at this going through, we will see some certain other things that we need to know. And one of them is when we talk about languages and we talk about computer codes and stuff like that, we talk about natural language, which is a normal language, as opposed to high-level computing languages. So hopefully I've given you the hint enough there. We've explained what machine code is. I've said it a few times, what it actually is. And again, I've said that Python and JavaScript and other languages are those higher level languages. So they would need a certain higher level, newer one of those words. And we've talked about assembler, machine code, and all the other things about which one are better. So I'm not going to try and give you the hints too much on those. And we're going to talk now about this next part. So I'm going to flick back to the presentation. And this is something that you could be asked quite, it's quite an important one. This is, I would say, the most important part. When you're doing software development or you become a coder, if you start to go down that road, I mean, this course is about thinking like a coder or thinking as a coder, but you don't necessarily have to become one. Maybe you're just the person that thinks like it. You've got another coder that does a job. Maybe you're the leader of all the coders and X, Y, Z. But what we're saying here is we need to be able to talk to coders or listen to clients about their requirements for a problem or a piece of software. And I'm going to go through some examples of some terrible requirements here, because a lot of time people aren't specific in what they do. So if somebody says this system must have good usability, I said, well, of course it should. Of course I wouldn't make something that is easy to use. But you need to actually be a bit more specific about what we're talking about. So don't just say these general terms. Define what they are. Use objective, measurable language. We sometimes call things qualitative and quantitative. And if you think about the word, a quantity is an exact amount and a quality is like up to someone's opinion. So if you say to people, it must have good usability, that's not definable. You must try and say stuff like, it's got to use a controller, or it's got to use the keyboard, or it's got to use a touchscreen. Start to think about things like that. Or it's got to have a good help menu, or it's got to have good documentation. We need to be very specific when we talk about software requirements. And there are certain standards. For example, if you post an image on the internet, you should put some text on it so that people that can't see very well have special computer software that can read that. So sometimes there are rules and standards that you must adhere to. And performance issues. I remember, and it was a really disappointing part of my life, that I learned a language called Flash. It was the most up-and-coming language on the internet. If you wanted to do something, you were a Flash programmer, spent a lot of time learning it, but it used a lot of processor power in the computer. And Apple decided to cut it. They decided to just go, no more Flash anymore. It's draining the batteries too much. So they actually cut it, and then the language kind of died. You can still do it, but you can't use it on mobiles. Apple won't allow you to. So there are things like that where you say it shouldn't use up too much memory, too much power. Be specific on what we're talking about. And be realistic. If you say, one of the things I was looking at recently was the Helldivers game that has come out of nowhere, Helldivers 2. And I was looking at it, and everyone's complaining that the servers can't keep up with demand because it's just got really, really, really popular. They used to have like 600, maybe 6,000 people maximum online, and now they've got 600,000 people online. So that you have to pay for that, right, to get those extra parts. They didn't know that they needed to grow that fast. They didn't know they're now going to have people on 24/7 because people are playing it around the world. But if they could solve those problems, they can make lots of money. So you can't just say to people, if I'm paying this amount of money, I need you on 24/7, but you're going to have to pay for things like that. Other things, it's got to be bug-free. I have never written a piece of code of any decent quantity of size without getting something wrong. Okay, so there will be testing. So you've got to factor that in when you're saying to someone to make a developer, or you're the person in charge of all the coders, how much time do we need to test this? And there are lots of computer games that got testing very, very wrong. And No Man's Sky is a classic example. I remember playing that on the PlayStation. Great game. But it was so massive, they didn't test everything. There was really weird things that happened, and people really fell out of love with the game because it had so many bugs. And I think Cyberpunk was another example of one of those games recently that did that really badly. So you need to make sure that you are factoring in that you need to test to get rid of those bugs, and that you need to have proper help for people, and that testing process is going to be clear. People also say things like make it accessible. Now, this is close to my heart. Both of my children are in wheelchairs, so when they want to play games, I want to make sure that I'm getting a game that's accessible. But even I don't think that every game can be the best accessible game ever. There are certain games that are reaction-based, so my son will struggle to play those. So we like to play games, the cat one that came out called Stray. He likes to do the problem-solving games that aren't specific on time or something like that. But also you just have to be clear on, try and get as many as you can, obviously. But if there is a specific type of people that want to go through and specify which type of accessibility needs to be clicked off for this game, then that's really important to do so. So you can't just say everything has to tick all the boxes. Easy to use, a terrible thing to say. Of course, you wouldn't design something that is there. Yeah, Grand Theft Auto 6, as I've just saw out the corner of my eye on a comment there. Absolutely. There are so many games out there where people know they weren't tested properly, or they're too difficult when they first come out. Elden Ring, loved Elden Ring as a computer game. Highly frustrating. It was my first Souls game I'd ever played. Didn't realize how hard they were. And, there's a famous saying on gaming now, which is just get good, right? There is sometimes nothing that stops just practicing on the game and getting better and better and better at it. But sometimes things are fundamentally wrong, and sometimes things are planned to be difficult or not. But as long as people know that going in, that's what we need to do. So make sure that, what does easy mean as well, right? If you're a computer programmer, what's easy to you might not be easy to everyone else. And I know people that are great at some things, but not technology. So what does good mean? Okay. So that's a really important thing to do. And people often say things as well, like it must be robust. What does that mean? That they're saying that it should never break, it should never do stuff. Yeah, okay, ideally. But as we've explained with things like Helldivers that got popular really, really, really quickly, sometimes you need a level of usability that is appropriate to the task. So when Facebook first came out, for example, it would have coped with maybe 100,000 people online at the same time. But at some point, it got really, really popular, and they had to scale that up and allow for millions of people online, hundreds of millions even, at the same time. So you put that into a level going forward. So I know, this has been not the most engaging of the subjects today, because sometimes they're more interesting. Sometimes we'll be doing some full-on coding and making things work. But sometimes we have to just be able to answer the questions that come up. So vague requirements, this is exactly the kind of thing that you might be asked in a multiple choice quiz. What does good requirements look like, and they have to be more quantitative than qualitative. That's a good word to remember to do. And you need to be realistic. You can't be vague. Your measurements should be specific. Don't just give these random kind of questions. So that's the end of that bit. And thank you for bearing with me, because I know that those parts aren't always the most interesting, but we are going to do in the quiz when we try and get the qualification for that. You want to go through here and you want to be able to answer those questions. So again, what's the difference between a compiler and an interpreter? We've said that. What is program specification? That's what we've just talked about there. The things that it must or mustn't have, but be specific about those things. And one thing we haven't talked about, but we mentioned that Grace Hopper came, what is a debugger? And a debugger, as we saw as we went through here, is something that will go through and tell you the errors of the program to make sure that we go. So on here, we have the high-level programming language, like your Pythons, like your JavaScripts and things like that. And then the last thing, which is probably the, not the hardest, but the one that may look scary when you do it, you just need to tick the box for this quiz to say, when you're testing, what does testing mean? What does design mean? What does programming mean? Analysis and enhancement. And you've got the right, only one for each of the boxes, and you go through. And then that quiz should be self-marking. And once you've done it, you can have a go. Now you can leave that and ponder, go back to the video and have a little look through, because this one was a bit more about the facts that we're learning as we're going through. Hopefully I showed you that coding back in the day with assembly language was hard, let alone machine code, which was even harder. But we are lucky to have compilers and interpreters do things line by line, as we can see here. And there are differences and pros and cons to those, but we might get to later on with those about how we go through. So we did say last session that sometimes they'd be quicker or faster each session. This one's going to be slightly quicker. Try and keep the harder to listen to fact-orientated sessions down to about half an hour, whereas the practical coding sessions that we can follow along with, we'll try and do that faster. So again, thank you for turning up. I see most people that turned up last week have turned up again this week. I think I've got an ending one this time. And as you can see from the camera here, I'm trying to up my game each time. We can see I've added some lights in so I can wear a white shirt and there's not white background, just running around the Digital Jersey offices trying to find some lights to make it better. And just trying to improve the quality of it. But do feel free to comment any constructive criticism. I do mind. I am very conscious that some of these sessions, as I said, will be a bit drier because we just need to learn some facts. So I'll try and mix them up each time between a kind of more interesting coding one where we're learning stuff and a fact-based session. And this one, again, will be now on the Digital Jersey webpage. So remember that you can go to Thinking Like a Coder, do the live link here if you remember that, or just go directly to Digital Jersey's YouTube page. And in the live session, rather than the home, if you go to the home session, you will just see possibly the live link. I didn't realize that comes up when we are live, but it will also have previous videos, but it's easier just to click the live chunk there. And I do remember, because I'm coming to the end now, and I will do this as I log off today, I will make a playlist for all of these, as was the suggestion last week for everybody. So you'll see last week's, there it is. You'll see this week's, these will start to add up, as well as the playlist, which I'll put on for Thinking Like a Coder. And we'll keep these sessions, like I said, short and sweet. So won't take it any longer. Thank you very much for taking part. Please remind everybody where you see them to keep coming back. And there's 15 sessions-ish, I think. We'll try and get it done with that. Maybe a few more revision-y type ones afterwards. And then we'll be able to do the exams or the online tests and book those going through to get a level 2, a kind of half GCSE qualification here going through, which I think, if you follow these videos, I don't think you'll have a problem doing. And even if you get the first one wrong, we could have a look again and try and have those another go and another go and another go. And I will do an online testing area that you can test your skills. So yes, thank you everybody for doing it. I will end with a similar view to as we came in, and see you next week. Do please like and subscribe. I should do that at the beginning. I'm obviously not a trained YouTuberist here. Do click those likes. They help these go forward. And do feel free to subscribe, because then you'll get notifications when these sessions happen. And you'll find it easier to find either on your phone or get the YouTube app for your telly so you can watch it on the telly. I think that's what I do at my house. Like and subscribe. So thank you very much. And see you next Tuesday at 4 o'clock as usual. Bye for now.